Welcome to lecture 32 of the course on high performance computing. You will remember that in the previous lecture we had looked at many examples of small pieces of C program code and tried to understand how they would perform for different kinds of cache organizations, and we got some understanding of how one could improve the quality of a loop in order to benefit from the spatial or temporal locality of reference through which the performance with the cache would be improved. Before moving into the next topic, I wanted to just quickly address two issues relating to caches, one relating to caches and one relating to pipelining, just to give us a slightly better idea about what happens in the processors which are currently quite popular. The first question relates to caches in the sense of, we talked about the CPU sending an address to the cache for lookup, and subsequently if it's a hit the data would come from the cache. But the question as to whether it was virtual or physical addresses that are used by the cache is of relevance. So we are looking into the relationship between the addresses that the cache uses, the cache hardware uses, and the address translation that we now understand the operating system manages but is done by a piece of hardware. So we understood that there are two possibilities as to how a cache could be built. The first is under the assumption that the cache is actually based on physical addresses. In other words, after the processor, the CPU, generates an address, it is translated by the memory management unit into a physical address, which is what goes to the cache. The second possibility is that the address which is generated by the CPU is directly used by the cache hardware. In other words, the virtual address is what the cache hardware uses for its lookup, tag checking, and so on. These are two different kinds of caches. You will note that in the second option there is the possibility of a cache miss, and in the event of a cache miss the data will have to be fetched from main memory, for which a physical address will be necessary, and therefore in the event of a cache miss in the second option there would be a need for the address translation to happen in order to generate the physical address for fetching the missing block from main memory into the cache. So these are the two kinds of caches we might expect to find, and I referred to the upper kind of a cache as a physical addressed cache because it is organized based on physical addresses. The cache hardware is organized to take in physical addresses. And the second, the lower example, the lower possibility, is what I refer to as a virtual addressed cache. And we looked at some of the negative aspects of both of these in the previous lecture. We understood that there are some benefits of the virtual addressed cache in that the time of a cache hit would be less than that for a physical addressed cache, partly because translation does not have to be done, but also for other reasons. But in both cases there are some negatives to the use of the cache organization, the physical and the virtual addressed cache, which leaves open the possibility that there is another option which might in fact be a good idea. And what the third option would try to do is to try to have some of the positive aspects of the physical address cache and some of the positive aspects of the virtual address cache. And the mechanism I am going to describe is something which will just try to use overlapping. In other words, it will try to do in parallel some of the steps associated with address translation and cache lookup. Now remember that in both the scenarios that we had set up, either the virtual or the physical address cache, the processor generates a virtual address. Now in the first option that we looked at, the virtual address went directly to the MMU for translation. In the second option, the virtual address went directly to the virtually addressed cache. But we could have a third option in which the virtual address goes to both to the MMU for translation and to the cache for lookup. Now in the event that there is a cache miss, we will still need to have the translation completed, and that's the reason that the virtual address is sent both to the MMU and to the cache. But these two are going to be happening in parallel. So while the translation is being done by the MMU, the early parts of the cache lookup can happen within the cache. Subsequently, by the time the address translation is completed and the physical address is available, the physical address can be used for the subsequent activities within the cache. For example, if by the time the translation has been done, the cache lookup, in other words indexing, has already been done, then with the physical address that has been made available by the MMU due to translation being completed, the tag checking could be done using the physical tag. And that is the idea which I am showing you over here. The idea that the virtual address goes both to the MMU and to the cache, while the virtual address is being used to do indexing into the cache directory. it is also being used in the MMU for translation, so that not too much time later the physical address is available and the physical address can be used for the tag comparison. And this will allow us to have something which is neither option 1 that we saw in the previous slide nor option 2 in the previous slide, but something new. And this in fact has some benefits over either option 1 or option 2. And I will refer to this as, I cannot refer to this as either a physical addressed cache or a virtual addressed cache, since it is both neither and both. It uses a parts of the virtual address for indexing, and it uses parts of the physical address for tag comparison. Therefore, the only good name for this kind of a cache would be to elaborate and say that it is a cache which uses virtual indexing and physical tagging. In other words, it uses the virtual address bits to index into the cache directory, but it uses the physical tag to do the tag comparison. So this kind of a cache would be known as a virtual index physically tagged cache, suggesting that the other alternatives that we had looked at could have similar names. And in fact, instead of referring to a cache as a physical addressed cache, one might talk of it as a physical index physical tag cache. What we called a virtual address cache up to now, in our second option, might more accurately be described as a virtual indexed virtual tag cache, in the sense that the virtual address cache that we looked at used virtual address bits to index into the cache directory. It also used virtual address bits to do the tag comparison, whereas the third option that we are just seeing is what we call a virtual index physical tag cache. Now, as it happens, the third option is what is used, the virtual index physical tag cache is what is used in the vast majority of processors today for the level 1 caches. Remember that we understand that in processors today, we expect to find both level 1 caches, which are relatively small but extremely fast, but backed up by level 2 and maybe level 3 and level 4 caches, which will be larger but slower. And this is done to offset the speed disparity, the growing speed disparity between processors and memories. So the indication that I am giving is that in today's processors, the level 1 caches actually use virtual indexing and physical tagging. And part of the reason for this is likely to be because we saw that the physical address caches suffer from large hit time. It takes a long time to get a hit in the cache because the translation has to happen before the cache is referred to. On the other hand, the virtual address caches have a much smaller hit time, and the virtual index physical tag cache will have that same benefit. It will not have many of the negatives associated with either of the first two options. So it is a preferable option and is widely used in the level 1 caches of today. Just to give us a better understanding of how these three differ, I'll just go through this diagrammatic mechanism for showing you what happens to an address in each of the three cases. And the numbers which I'm going to be using for the different bit fields, the sizes of the different bit fields, will assume a 64 kilobyte direct map cache which has 32 byte blocks. In addition, since we are also going to be talking about address translation, remember that address translation happens on the involves mapping a virtual page number into a physical page number. So suddenly it also becomes important to know something about the page size. So this will also enter the calculations or be a factor in the diagrams that we are going to look at. Okay, so we'll start by looking at a physical index physical tag cache. And when we think of a virtual address, we, from the perspective of address translation, recall that a 32-bit virtual address would have least significant bits that we call the page offset bits, and most significant bits which we call the virtual page number from our discussion of virtual memory. How many bits are used for the page offset? That would be determined by the page size. So if the page size is 16 kilobytes, there would be 14 bits of page offset. 14 is log base 2 of 16k. The remaining 18 bits are the virtual page number. Now if we are talking about a physical index physical tag cache, then this address will have to be translated by the MMU before it goes to the cache. So what does the MMU do? The MMU actually translates by replacing the virtual page number by a physical page number. And the page offset bits, the least significant 14 bits, are not affected by the translation. Therefore, if I show you what the MMU does, it would amount to something like this. It translates the virtual address into a corresponding physical address. The virtual and physical addresses are identical in their least significant 14 bits for this particular example, and they differ only in their most significant 18 bits, because what the MMU did was it replaced the virtual page number by the corresponding physical page number using the information inside the relevant page table entry, possibly available in a translation look-aside buffer, which is part of the processor. Right, so this is the address. The physical address is what is going to be used to access the cache in the physical index physical tag cache, and it is this address which we have to look at in the light of the cache perspective on addresses. So this is now going to be viewed as a cache block offset, which is going to be 5 bits in size because the block size is 32 bytes. It's a direct map cache of 64 kilobyte size with 32 byte blocks, from which we can calculate that the number of index bits required is going to be 11, and the remaining bits, which in this case will be 16, will be the tag bits. So the 11 index bits are used to index into the cache directory, and then the tag comparison is done. The valid bit is also referred to, and if all of these are indicate that this is a cache hit, then the offset bits are used to select the correct bytes out of the cache RAM to satisfy the processor's request. So you will notice that for this particular example, the index bits are coming partly from the page offset. Just look at where the 11 bits are coming from. The bulk of them are coming, 9 of them are coming from the page offset bits, which are common to the physical address and the virtual address, and only 2 of the bits are coming from what is now the physical page number side of the address bits. Okay, now if we now move to the second possibility that we had, the virtual indexed virtual tag cache, which is what we were calling the virtual address cache until now. So in this case, the address translation may not happen. The address translation is not required if there is a cache hit. So the virtual address itself is viewed in the light of 5 bits of offset, 11 bits of index, and 18 bits of tag. The index bits are used to index into the cache directory, and then the virtual page number provides the tag bits which are used for tag comparison, and if the indications are that it's a hit, then the correct bits are picked out using the offset. Now if it is a cache miss, then the MMU does the translation and we get the physical address which goes to memory. So in this case, once again, you'll notice that all of the 11 bits which correspond to the index, 9 of them are coming from the page offset bits, and the remaining 2 are coming from the least significant bits of the virtual page number. Now you may be wondering, why am I pointing out where the bits of the index are coming from? This relates to something that we were doing in the early parts of the previous lecture. You'll recall that when we were talking about how to figure out the number of hits, the number of misses for a loop that is of interest to us from a program that we may be running on a computer, we used information about the addresses of the arrays, array A or array B, etc., in order to calculate what the index bits are, in order to get an idea of whether there were conflicts, hits or misses, etc. And at that point we were assuming that the cache was indexed using virtual addresses. We were assuming that the addresses which the compiler generated, in other words the virtual addresses, were what were being used for indexing into the cache and for the tag comparison. And that is a perfectly legitimate assumption as far as the virtual index virtual tag cache is concerned, because it is virtual addresses that are used for this purpose in such a cache, but is, as we now see, not entirely correct as far as the physical index physical tag cache is concerned. I've gone back to the previous slide. So you'll note that in our calculations, in our estimates for the various kinds of small examples that we looked at, we did the calculation assuming that they were virtual addresses, but in reality the cache was indexed into and the tag comparison was done using physical addresses, if we're looking at the example of the physical index physical tag cache. And what difference would it have made in our estimates of hits and misses? We noticed that the index, primarily the calculations that we were doing in looking at the reference sequence that we had and so on, was to try to find out what the index bits were for a given memory reference. We now see that for the example that we have, for the sizes that we're looking at here, of the 11 index bits, 9 of them are coming from the page offset region of the address, and 2 of them are coming from the virtual page number or physical page number side of the address, which means that when we made the assumption that we were using virtual addresses, there would have been some 2 bits in those 2 positions, but in reality when the cache is looked up, there will be some other 2 bits depending on how the address translation maps the virtual page number into the physical page number. And therefore a calculation of those index values would have been wrong in the case of the physical index physical tag cache, because we were working with virtual addresses. We had no means of knowing what the physical addresses were. The physical address of a particular page will change as the page moves in and out of memory depending on the occurrence of page faults. We have no means of knowing what the physical addresses are. However, once again, if you think about what we were doing in our calculations, we were trying to cause offsets to happen to prevent index bits from being exactly the same. And these were in situations where we were concerned about neighboring or contiguous regions in memory, such as the example we had of the array A and the array B, the vector A and the vector B, which had assumed base addresses of hex A000 and E000. And under the assumption that these are actually fitting on the same page, you will notice that there is no problem. So if the data that we are talking about would actually fit on a single page, then this problem does not arise at all, because all the difference in the different addresses will occur within the page offset bits, and therefore there is no problem as far as we are concerned from that perspective. However, if the data is larger and actually causes the difference in the index bits to happen between these two bits, then the calculations that we were doing would be not precisely correct. And therefore, we have to understand that what we were doing was just estimating the behavior as far as the hits and misses were concerned, in the case of this being a physical index, physical tag cache. Okay, now moving to the third option that I just introduced in this lecture, which I referred to as the virtual index physical tag cache. You'll recall that the virtual address is what is used to index into the tag directory, to index into the cache directory. So it is the 11 bits from the virtual address that are used to index. Subsequently, the address translation happens and we get a physical tag, which is what is used for the tag comparison. The physical tag is used for the tag comparison. And this is what will happen in the case of the virtual indexed physical tag cache. So this is what we should understand is going to be present in the bulk of the L1 caches in processors today. And this too will have the problem that we referred to in terms of the tag bits will be a little bit different if we did our calculations for the behavior of our programs based on virtual addresses. However, since the indexing is going to be using virtual addresses, our calculation of index conflicts is going to be accurate. And therefore, there was no need for us to worry too much about the technique that we used in the case of analysis of the simple loops if we were dealing with virtual index physical tag caches, since our calculation of which different pieces of data, like the vector A, the vector B, whatever, would actually have conflicts as far as the index bits is concerned, would have been accurate in the light of our using virtual addresses, if it was a virtual index physical tag cache. Right? So hence, this additional information would be important to us if, for example, we get more details about the nature of the L1 caches in the processors that we are dealing with. And the techniques that we were using are perfectly legitimate for a virtual index physically tagged cache or a virtual index virtually tagged cache, but would only be estimates as far as the physical index physical tag cache is concerned. Now moving right along, I also wanted to make a few comments about the second question, which will give a rough idea about a few other developments that have happened in the area of pipelining. So we talked about pipelining in the light of the 5-stage example. There was the pipeline where there was instruction fetch, instruction decode, execute, memory operation, and write back. And the question is, are modern processors really built using pipelines of that kind? Now, it turns out that the kind of pipelining which we saw was getting performance benefit by overlapping the execution of many consecutive instructions. That's why we had a 5-stage pipeline. You'll recall our notation from many lectures back. The 5 stages, one for fetching instructions, one for decoding instructions and fetching operands, one for use of the ALU, one for the memory operation, cache access, and one for updating the destination register. And while one instruction is being fetched, another instruction could be decoded, and a third instruction could be using the ALU, a fourth instruction could be accessing the data cache, and a fifth instruction might be updating its destination register. In other words, there was substantial improvement in performance because of the overlap of the execution of consecutive instructions. It's overlap in the sense that each of the instructions is using a different piece of the processor hardware. Now, modern processors would actually be much more aggressive in their attempts to improve performance by using more than just overlap. And one of the directions which almost all modern processors use is to exploit something known as instruction level parallelism. And this is such a frequently used and prevalent concept that it is typically abbreviated as ILP, ILP standing for instruction level parallelism. And the general idea of instruction level parallelism is that rather than just overlapping the execution of instructions, it should be possible to execute instructions in parallel with each other if they are independent of each other. In other words, what we mean by in parallel is that 2 instructions might actually be fetched at exactly the same time. 2 other instructions might be being decoded at the same time. 2 instructions might be executing at the same time. And this is, we understand, possible if the 2 instructions that I'm talking about are actually completely independent of each other. So this would clearly provide a much greater level of improvement in performance, since instead of having 5 instructions occupying the processor hardware at a time, if I have 2 instructions being fetched, 2 being decoded, 2 being executed, etc., I actually have 10 instructions occupying the processor hardware, and therefore the rate at which instructions would complete execution could be substantially higher. And this could lead to additional improvements in the performance of processors. So today we find that most processors in personal computers or laptops that you are using would be exploiting this kind of parallelism in their pipelines, and they would therefore be called ILP processors, processors that exploit instruction level parallelism. Now, the challenge in the design of an instruction level parallelism processor is being able to identify the instructions which can be executed in parallel. It is only if 2 instructions are independent of each other that they could conceivably be executed at the same time in parallel. And there are 2 approaches that modern processors, the different kinds of modern processors use in order to undertake this activity. The first approach is to actually design the hardware so that the hardware itself analyzes the independence between instructions, and if there are dependencies, it keeps track of the dependencies in order to make sure that instructions which are dependent do not move through the pipeline and cause the execution of the program to be incorrect. So the management of the instruction level parallelism is done by the hardware in this first approach. And the name given for these kinds of processors is to call them superscalar processors. The general idea that one could have in mind when thinking of the superscalar processor is that until now we had a picture of a processor which might have a pipeline processor which might look something like this, and there could be 1 instruction being fetched, 1 being decoded, 1 being executed, 1 using cache, 1 being written back. But in the case of a superscalar processor, it's conceivable to try to think of the same processor as having, let's say, the capability of not only fetching 1 instruction but of fetching 2 instructions. So I might think of it as a processor which has hardware complicated enough to fetch 2 instructions, complicated enough to decode 2 instructions, to execute 2 instructions, to allow 2 instructions to be accessing cache at a time. Right? So in some sense, one could think of the superscalar processor as this hardware which is like the pipelines that we saw before, but has this additional capability at each stage so that more than 1 instruction can be processed in that stage. And that will clearly require additional hardware. But this gives us the additional necessity to understand the processor as having an additional dimension. Until now we talked about the processor as having many pipeline stages. I talked about the n stage pipeline, right? And we saw that an n stage pipeline could conceive, in this case we have a 5 stage pipeline, but in general you could have a 20 stage pipeline where n is equal to 20. And the speed up, the amount by which this pipeline could speed up the execution time of a program was related to n. So this was one dimension, and we talked about this as the pipeline depth. N was the pipeline depth, the number of stages in the pipeline. We now understand that in superscalar processors there's this additional dimension, which is the number of instructions that could be fetched or decoded or executed or written using cache or written back at a time in parallel. So in the example that I mentioned, that it looked like 2 instructions could be in any one of these stages at a time, and that is not depth but what is referred to as the pipeline width. So that is what is referred to as the pipeline width. And in the example that I just mentioned, the idea was that the pipeline width was 2, and we could imagine that there could be pipelines which have a width of 4. In other words, they have the capability of actually executing 4 instructions in one cycle, or completing 4 instructions in every cycle. And you could understand that if there was a pipeline which had a width of 4, then it could conceivably have 4 times the performance of a pipeline of width 1. A pipeline of width 1 would be the simple kind of pipeline that we looked at in some detail. And many of the processors that you may be familiar with today have widths of 2, 3, or 4. So this is one possibility as far as exploiting instruction level parallelism is concerned, approach 1, where the hardware is responsible for the management of the dependencies and parallelism, and such processors being called superscalar processors. The second possibility is that the job of identifying independent instructions could be done by the compiler. In other words, the compiler could analyze the program before the program is executed, identify instructions which are independent of each other, and in effect pack those independent instructions together, so that all of the independent instructions in a given cycle could be, if packed together, could be moved through the pipeline together. And this kind of an approach is what is known as the VLIW, standing for Very Long Instruction Word Processor approach. The term very long instruction word comes from this idea of actually packing many independent instructions into one mega instruction of some kind. And consequently, one could think of the larger instruction, which is the packed version. If it has four MIPS1 instructions packed into one instruction, it will obviously have to be of a larger size, hence the name. And there are some commercial examples of VLIW processors as well. So this is just a minor addition to what we have talked about in terms of pipelining. Modern processors do more than just the simple kind of pipelining we talked about. With this, I would like to wrap up our discussion of the cache memory. Our next topic, just going through the agenda sequentially, refers to program profiling. And without further ado, we'll move into program profiling. Okay, now in general in this topic I'm going to talk about two things. One is what I'll call timing, and the other is what I'll call profiling. And profiling is actually something that we've been talking about before without using this term. And it is essentially the activity of identifying the important parts of your program. And what we mean by important parts are the parts of your program where the most time is spent, because it is these parts of the program that you would want to look at more critically in trying to optimize your program. For example, if I have a very large program, thousands and thousands of lines in size, then it would clearly not be possible for me to do, for example, pipeline analysis or cache analysis of the entire program, because we saw that to do cache analysis, the number of hits, the number of misses that would be generated when the program executes, one had to go into some detail into the way that the different variables, the addresses associated with variables, etc., interacted with each other. And therefore, if one could, on the other hand, identify smaller regions of the program which are in fact significantly important, then one could concentrate one's activity, optimization activity, on those smaller regions of the program and get possibly a very good benefit in terms of improving the execution time of the entire program. So the activity of identifying the important parts of your program from the perspective of wanting to spend your optimization efforts on just those important parts is what is typically referred to as profiling. And it's obviously going to be important to us. We've understood a lot about the hardware and the software side of what happens when our program executes, but in order to do something about improving the performance of our program, we may have to know which parts we should concentrate on. And therefore, this is a critical part of high performance programming. Now, you'd guess that an important part of doing profiling might be having the capability of getting time estimates, or knowing the amount of time that it takes for your program to do something. And timing is in general the term given for determining program execution time. But I could also refer to timing as the activity of identifying the amount of time spent in some part of my program. For example, if I've identified a particular function of my important as being important, I may want to know how much time was spent just in that function. I may not be too concerned about the total program execution time. The total program execution time, I might be more interested in getting the time as far as some important part of the program is concerned. Therefore, associated with profiling, there may be the need to know something about timing. And hence, we'll spend 1.5 lectures or 2 lectures on understanding concepts and capabilities for doing things like these, timing and profiling of our programs. Let me start with timing. Okay, now, our objective here is to measure the time spent in specific parts of my program. And it could be that I want to know the time spent in executing the entire program. It could be that I want to get an idea of the time spent in one of the important parts of my program, such as a particular function or a particular loop. And what could I mean by the different parts of a program? Well, we've seen examples where there were loops that we analyzed. So a loop like a DAXP loop or a vector sum loop, etc., could be examples of loops. The other example that I used were I might be interested in trying to improve one particular function of my program. So in general, when I say parts, I could be talking about functions or loops. And At this point, I will just remind you that when we talked about time earlier in this course, we distinguished between a few different kinds of time, because we understood that on a machine where there is only one CPU, the operating system is creating the illusion of many programs being able to share the CPU by actually sharing the CPU time among the different processes that happen to be in memory. And therefore, there was a need for us to distinguish between at least two different concepts of time. One was the actual elapsed time, as we would see on a clock on the wall, and that is referred to as the real wall clock or elapsed time. And the other is this virtual process related time, the amount of time of the CPU that a particular process actually got. And it should be possible for us to find both of these times, and the mechanisms that we are going to look at will have to be identified as providing you an estimate either of the real time or of the virtual time. And unless you are aware of what a particular mechanism is giving you, the time itself may not be of much value to you in figuring out how your program is behaving. Therefore, in doing a timing estimate, or in doing timing experiments or timing runs of programs that you are interested in, there are a few decisions that you have to make. The first decision that you have to make is, what time are you interested in measuring? Are you interested in measuring the real wall clock or elapsed time, or are you interested in measuring the virtual CPU time? And there may be some situations where you are interested in the first and some situations where you are interested in the second. So this is the first decision that you have to make. And secondly, another decision that you have to make is, how fine an estimate of the time do you need? Would it be, for example, would it be enough if you got an estimate that was accurate to the nearest second, or do you need an estimate that is accurate to the nearest clock cycle, nanosecond? So that is another decision that you have to make, and you clearly understand that the decision has to be made in order for you to use the correct mechanism for measuring time. Different mechanisms will be provided. Some of them might be capable of providing you elapsed time only accurate to a second. Others might be capable of giving you CPU time accurate to the nanosecond, but you have to pick the correct mechanism depending on what your objective is. So you first have to decide what your objective is. Once you have decided what your objective is, you look for the correct timing mechanism which satisfies your objective. In other words, if you are looking for elapsed time, you look for a mechanism that can give you elapsed time measurements and of the appropriate accuracy granularity. Okay, now let's just look at a few of the time related mechanisms that you will find on Linux or Unix systems. Now, one mechanism which some of you may have come across and may even have used is what I will refer to as the time command, and you may have in fact used it. And the way that you use it is that in response to the shell prompt, if your intention is to find out the amount of time that it takes in the execution of, let's say, the program a.out, then rather than just executing a.out, which you would have done like this, you execute a.out through the time command. In other words, you type time space a.out, and now the time command will cause a.out to be executed, but it will give you in return information about how much time it took for a.out to execute. Let me just give you a few examples. So let's suppose that in response to the %shell prompt, I typed time ls. Those of you who have used Linux or Unix systems will recognize ls as a command which can be used to get a listing of the files within a directory. We will learn more about files and directories a little later, but ls is a command which gives you some information about the different files which are available for access. Now, when you type time space ls, obviously the ls command will print out the information that it is supposed to. I am not going to show you the output of the ls command. I am just going to show you the possible output of the time command. I believe this was taken on a Unix system, this particular output. So you will notice that the time command is giving me three pieces of information. One is labeled as user, one is labeled as system, and one is labeled as elapsed. And therefore, we would understand that the time command is giving us elapsed time, but in addition it is giving us CPU time or virtual time. So the elapsed time is obviously the elapsed or real or wall clock time that we talked about earlier, whereas the other two times which have this breakup into user and system are what we refer to as the virtual or the CPU time. So the time command is giving us both. It tells us both how much time was spent in terms of the virtual timeline of this particular process in user mode, and that number was so small that it is registered as 0, as well as the amount of time that was spent in the execution of ls in system mode, and that is given as 0.002. I believe the unit here is seconds. In addition to this, it gives us the amount of wall clock time, the actual elapsed time, the amount of time I would have observed if I had looked at a wall clock before and after the time command was executed, and that is given as 0.003. So in this particular case, we understand that the bulk of the time of execution of the ls command was spent in system mode. Very little, practically no time was spent in user mode, and the bulk of the elapsed time and the relationship between the elapsed time and the amount of time spent in the virtual mode is fairly close. Now let's just look at another example. This is a more complicated example. Here I'm going to use a time command to find how much time it takes to execute the command man csh. Now what is man csh? We've come across csh before. I could have run the same command by typing man csh. We've come across csh before. Csh was one of the shells that is available on many Unix and Linux systems. It's a command interpreter. What about man? Well, man is common in Unix and Linux systems as a command that can be used to read a manual entry. So man stands for the manual, or a book which contains information about the different commands, and that's available online. So when I type man csh, in effect what I get is a listing on the screen, a printout on the screen of the manual entry for the csh command. And this is a very long manual entry, and typically when you type man csh, you do it with the purpose of reading some section of the manual entry, and therefore you suspect that if somebody did a man csh, they would spend some time reading the page as it is on the screen. How will that reflect itself in the output from the time command? If you look at the output from the time command, and once again I'm not showing the output from the man csh because that would be a 30 or 40 page document, so we don't want to look at that on screen. But you'll notice that the user time is no longer 0. There is a significant part of a second spent in user time. There's a small amount of time compared to this which is spent in system mode, and a fairly large amount of time that is spent in actuality if I look at the elapsed time. So I believe this is 15 seconds of time, of which 0.032 seconds are spent in system mode and 0.268 seconds are spent in user mode. So if I look at the sum of these two times, it adds up to about 0.3 seconds. And I look at the amount of time that was actually spent in elapsed time, it's 15.48 seconds. In other words, I spent 15 seconds reading the manual entry, and the actual amount of CPU time, both in user mode and in system mode, that was spent on this command was only a third of a second. So where was the remaining 15 plus seconds spent? It was obviously spent because I as a user was reading this information off the screen in order to understand something about the use of CSH, and that is reflected in the elapsed time but not reflected in the user time, in the virtual CPU time, because during the time that I am not interacting with the program, the process itself might in fact not be running. It might be in a waiting mode. You might get blocked. So this is revealing to us and gives us some idea about what kind of time we should be looking for depending on our requirement. Okay, so in effect, the summary is that the time command reports both real elapsed wall clock time as well as CPU time or virtual time, and as far as the CPU time is concerned, it gives you a breakup between user mode and system mode. Now another command which might be useful to us is called get time of day, and I'm using this notation because get time of day will be invoked like a function from within a program. So in order to understand how to use get time of day, I told you about the usage of the time command by just showing you how you could use the time command from the shell prompt. The get time of day we are now told is a function, which means that we will be using get time of day from within our program. We will write a program which can call get time of day, and therefore I tell you a little bit here about the get time of day function. It has some parameters, and the details about the structures used in the parameters as well as the function itself are available in an include file. So if you were to use get time of day, you would have to include this include file in the program. Now if you actually looked at the time while struct and you would look at it inside the sys/time.h include file, you would see that the time while struct contains two fields, one of which is a field that reports seconds and the other is a field that is labeled microseconds. The fields are called TV_, TV for time val. So, TV underscore sec and TV underscore microsec or usec. So, clearly this is a structure which contains an or something to do with time to the granularity of microsecond apparently. And the question is, how do we use this? In order to use it, we have to know what the meaning of the value that it returns is, and this information I am giving you in that yellow block up at the top. So, what get time of day reports, or what it returns as its return value in the struct time val parameter, is the real time that has elapsed since 0000 Greenwich Mean Time on the 1st of January 1970. And the manual entries that you read in connection with get time of day will refer to this instant in time as the epoch. So, basically what this is returning to us is a number of seconds, the number of seconds that have elapsed since 0000 Greenwich Mean Time on the 1st of January 1970. Now, that is a rather curious thing to return, but you will understand that if I call get time of day now, I will get the number of seconds that have elapsed since 1st January 1970, and then if I wait some time and I call get time of day again, then I will get the amount of time that has elapsed once again since 1st January 1970, and the difference between these two return values will tell me how much time has been spent by my program in between, and that I can therefore use the get time of day to estimate the amount of time spent in a part of my program. Okay, so, the idea is that I could use get time of day by inserting calls to get time of day in my C program before and after the regions of interest to me, in terms of the region, a particular region of interest to me in my program, which I want to know how much time I was spent in execution. So, let us consider a C program, and let us suppose that there is some particular region that I am interested in. I am interested in this region. I want to know how much time was spent executing this part of my program. So, what I can do is I can set up two time val structures, one called before and one called after. I can call get time of day passing the parameter before the region of interest to me, and call get time of day passing the parameter after the region of interest to me. Subsequently, I can compute the difference between the sec fields, the second fields of the after structure and the before structure to find out how much time was spent in that particular region of my program, and I could print that out using a printf statement in order to actually get output, which I could subsequently look at to understand how much time was spent in this region of my program. Therefore, you can use get time of day by inserting calls before and after, and subsequently computing the difference between the after value and the before value in order to measure the amount of real time. So, the important thing to remember is that what we are talking about here is elapsed time. Get time of day returns a real or elapsed time or wall clock time value. Okay, now the next question is whether there are other timers which can give us good estimates as far as high resolution or very nanosecond type of estimates of how much time are being taken by in parts of our programs. And just to quickly give you an idea about this, I would like to mention that almost all modern processors provide a mechanism which can be used for this purpose, and these mechanisms are hardware. They are built into the hardware, and they basically return a count of the number of cycles that have elapsed, and that therefore one could use a hardware cycle counting mechanism, and if one knows how much time is spent in one cycle of that processor, for example, if I know that this is a 1 gigahertz processor, then I know that one cycle is equal to 1 nanosecond, then by counting the number of cycles or by using a cycle counting hardware mechanism, I can get very accurate real estimates of real as in real elapsed wall clock estimates of how much time was spent in a part of my program. Now, how would these mechanisms be made available to the programmer? I have suggested that they are available in the hardware. Now, if such a mechanism is available in the hardware, we would suspect that the CPU would contain a special purpose register that is incremented every clock cycle, and that it is by referring to this register that the cycle counting mechanism works. So, if the processor has this register and the register is incremented every clock cycle, then as long as there is an instruction using which we can read the value of that register and print it out, then we can use this mechanism in our programs. So, in addition to the special purpose register that is incremented every clock cycle, all that the hardware has to provide is an instruction to read the value that is in that register. And this is, as I said, available in almost all modern processors. For example, the Intel processors have something called the timestamp counter, They don't call it the cycle counter, they call it the timestamp counter, or TSC, timestamp counter. And there is an RD, or read TSC instruction, RD TSC instruction, using which one can access the timestamp counter. This is not a privileged instruction, it's an ordinary user mode instruction. And almost all processors today have similar mechanisms. So one could use this instruction before and after the region of interest in the program, and by calculating the difference between the two and knowing the amount of time that a cycle is, one can get very accurate estimates of how much time is spent in a region of the program. Okay, now with this idea about timing, we understand that there are mechanisms at the level of a full program, such as time. There are mechanisms at the level of parts of a program, such as get time of day. And there are even more accurate mechanisms which will give us cycle counts of parts of a program, such as the hardware timestamp counter type mechanisms. Now let's go back to the primary question of interest to us, that relating to profiling. How do we find out the important parts? How do we identify the important parts of our program? Now, in order to do this, we could of course use the timing mechanisms that we have seen surrounding the different suspected important regions of our program by calls to get time of day and calculating the differences. We could do this for all the regions of our program and then identify the important regions by such a mechanism. But this would be a mechanical process for which we would have to include the calls to get time of day at various points in our program, and might be an inconvenience for extremely large programs. So what we would prefer instead is some kind of a mechanism which does this automatically for us. In other words, we would like to have access to a tool which does the profiling for us. And if there was such a tool, it would obviously be called a profiler. So going back to the slide, a profiler would be a tool that helps you identify the important parts of your program so that you can concentrate your optimization efforts on those important parts of your program. And there are fortunately many different profiling tools that are available. And the word profile is used to refer to a breakup, typically of execution time, across the different parts of the program. So you use a profiler to get a profile of your program. The profile may tell you how much time is spent in each of the functions of your program or each of the loops of your program. And using that profile, you can quickly identify what are the important functions or the important loops of your program. Now, as I had mentioned earlier, you could do this on your own by adding statements into your program, such as calls to get time of day. But an alternative is to get this done for you by a profiler to save yourself the nuisance of having to do this insertion of additional statements into your program. The insertion of those additional statements in the program is what might be referred to as instrumentation. Instrumentation itself is a discipline, it's a branch of engineering. What one studies in instrumentation is the construction of instruments. Instruments are devices which can be used to make measurements. And if you think about it, the profiler that we're talking about here is in fact a tool which is being used to make measurements through which we identify the important parts of our program. And the way that the profiler could work is by adding statements into a program, and therefore the statements which are added are the instruments through which the profile is obtained, and hence the process of adding those additional statements is referred to as instrumentation. So we are currently trying to understand something about the profilers which will do this for us automatically, so that we don't have to add the instrumentation by ourselves. Now there are several different profiling mechanisms that are available on the typical system, and these profiling mechanisms will differ in a few ways. One way that they'll differ is in the level of granularity that is supported. And to some extent we can think of the granularity as being the size of the important region that we're talking about. I talked about using profiling to identify the important parts of our program. So how big is a part? That is what we're talking about in this section about level of granularity. So there are some profilers which give you information at the level of functions. So the level of granularity is the function level, and they would be called function level profilers. There are some profilers which give you information at the level of statements, or for example lines of a program, and they may be called statement level profilers. There are yet other profilers which give information at other levels. One of the more popular kinds of levels of profiling is something called the basic block level. And roughly a basic block is a sequence of contiguous instructions in a program with the property that that sequence of contiguous instructions in the program has a single entry point, which is the first instruction in the basic block, and a single exit point, which is the last instruction in the basic block. So in some sense, a basic block is some series of instructions in a program such that you enter the basic block only from the first instruction and you leave the basic block only from the last instruction. In other words, if a particular basic block is a series of instructions, so it might start with a load word instruction, then there might be an add instruction and so on. But as far as the basic block is concerned, we get by the definition, we understand that if the first instruction in the basic block is executed, then all the instructions in the basic block will be executed exactly once. So that's why this is a nice way to look at a program. One could, rather than thinking of a program as being made up of functions or just statements, at a lower level one could think of the program as being made up of basic blocks, and hence some people like to use basic block level profilers. So profiling mechanisms might be available at different levels in the light of the granularity, the size of the important parts that could be identified. And in general, profilers may also differ in the nature of the kind of data that they give you. Until now we were assuming that we were interested in finding the amount of time that was spent in executing an important part of our program. But there could be other considerations that are important other than time. For example, one important kind of profile data might be a breakup of the amount of execution time spent in the different parts of my program, or how much time was spent in a particular function. But in addition to this, it might be adequate if I knew how many times each function was executed. If, for example, I knew that a particular function DAXP was executed 30,000 times and all the other functions in the program were executed only 1 or 2 times, then that would be possibly enough reason for me to try to concentrate my attention on the function called DAXP. So even just a count of how many times a function or a statement or a basic block was executed might be of value to us, and that would be a different kind of profile data. Rather than getting a breakup of the number of seconds spent in each function, I may just get a feedback on the number of times each function was executed, and that might be a different kind of a profiling mechanism. So there will be different kinds of profilers. They will differ in their level of definition of important part of program, and they could differ in the kind of information that they provide in terms of trying to classify something as important. They could be based on times, they could be based on counts. Now what we are going to do is, we are actually going to look at 2 specific profiling mechanisms. We are going to look at exactly how they work. We are going to look at one of the mechanisms we are going to look at is at the function level. The other mechanism we are going to look at is at the basic block level. We will understand the mechanisms that are used behind the scenes. We will understand, therefore, the guidelines which should be taken into account in trying to use these mechanisms. And we will proceed by looking at the function level profiling mechanism in the next lecture. I'll stop here for today. Thank you.